Okay, in the previous exercise, we have learned to calculate the confusion matrix in the case of a diagnostic test, in the case of a virus infection. And we have introduced some measures like sensitivity, specificity, recall, etc. Now, the derivation of the confusion matrix in that case, it was done under the assumption that the result of the test is very sharp, in the sense that when I read the outcome of the diagnostic test, then I see clearly either a positive result or a negative result. Now, this is the case, for example, for the PCR test of the COVID virus. Because what does the PCR test precisely do? The PCR test try to detect the genetic material of the virus. Then if this genetic material is found, then it is amplified, and then it gives clearly a signature of a positive outcome. For this reason, it is very unlikely that a PCR test will give a false positive result, because of course if the material is not detected, it cannot be amplified, and then this cannot lead to a positive outcome. So this means that we have seen that when the false positive is almost zero, then the true negative rate, which is defined as the true negative divided all the observed negative, people which are negative, then you see when the false positive is very small, this is very high. And that's indeed the case of the PCR test. And that was also the case in our example before, because you know that this is also the true negative rate, the specificity. Okay, but for sure in the case of the COVID PCR test, then because the probability for false positive is very small, then the true negative rate, the specificity, must be very high. On the other hand, if the probability for a false negative is, in the case of the PCR test, much more probable, because what happens is that it can be that the virus is present, but in a very small amount, and then the test cannot find the genetic material of the virus, and even amplifying this material, it cannot be seen, and then this leads to a false negative result. So basically what we have is, in the case of PCR COVID test, the false negative probability should be larger than the false positive. Nevertheless, this it is not very high anyway, and this, we know that the true positive rate, this assures the true positive rate, which is the sensitivity defined as true positive divided all the people which are actually positive, which are infected, observed, then this must be very high. And that was also the case here. You see, we remember that this probability, the probability to be positive given that you are infected, actually was the true positive rate, or we call it sensitivity. Okay, so you see that the example that we had is basically a bit representative of what is a COVID test, with the only difference that in the case of PCR test, we expect the false positive probability to be smaller than the false negative probability, because false negative results are much more likely in the case of the PCR test, because of this amplification, detection and amplification mechanism. But okay, this is not true for all the tests. So basically what happens is that sometimes especially when you don't have this amplification mechanism, or where somehow the presence of the virus can be deduced from the detecting some amount of let's say antibodies or stuff which can be basically produced by also by other effects, then the situation is different, in the sense that okay, maybe you can detect some concentration of some quantity, and at some point you have to decide when this concentration is enough to conclude that the virus or the test is positive. Okay, so there is some I would say degree of freedom in choosing a threshold for such some quantity, for this quantity, which decides if the result of the test is positive or negative. Okay, it is introduced to the general problem of binary classification. So we want now to reconsider the problem of the confusion matrix applied to a situation where basically the result of the test depends, I mean, interpreting the test as positive or negative depend on some threshold that we will call cutoff. And we do this moving from this example of the diagnostic test to in another context, namely to a problem of marketing. So basically what we have is this situation. We have an airline which works as a tour operator, and they want to advertise some new format holiday trip reserved only to people who already flew with them. And basically then you would address all your clients, and in order to make this advertising campaign, and with the hope that they will join the new offer. But of course, to reach all your clients, that they have at least a flight at least one time with you, on that there are so many, maybe it's too expensive. So what you want to do is, this is some kind of targeting problem. You would like to be able to address only people where the probability that they will buy this offer is higher. So suppose that you want to achieve this. What you can do, you can take a sample, and then in this case, basically this company has considered a sample of the 806 clients, and you propose them this offer, and then you measure basically how many of them they buy the offer and how many not, and you classify basically these 806 clients in classes, which are the classes basically given by how many times these clients already have flown with your company. So for example, we see that among the clients which flow only 2 times, basically there were 34 clients who buy the offer, didn't buy the offer, and 3 clients that they actually did, and so on. Okay, you can argue that this sampling is quite unhomogeneous, but okay, this is more realistic than what you think, because many times it can be that these data were very difficult to gather, or the data were incomplete, and these are the only data that you can rely on. In any case, okay, this is the situation. So you have this sample, and you have classified these clients in classes which count how many times they already have flown with your company, and for each then you have basically detected if they buy the offer or not. So if we inspect this table, then we see that the larger it is the number of times that the clients they've flown, the larger becomes the probability to buy the new offer, and the other way around. I mean, for example, for clients that they have flown very few times, then the probability of don't buying the offer is larger. So there must be at some point we want to decide some kind of the cutoff. Where is the cutoff in these classes between 2 and 20, where we can say that we expect as predicted value that the client will buy the offer. So the exercise is indeed to create a confusion matrix for a number of flights of 10 or more. So just choosing the cutoff at 10. Moreover, if we want to establish the connection with the theory of the confusion matrix, then we have to define what is considered as success, and then we will take this when the client buys the offer. Okay, and failure, it will be when the client is not buying. Okay, so in this confusion matrix, then success means that to buy, and failure means do not buy. What is still missing in our table in order to complete the confusion matrix is to define the predictions. So when a client is predicted in success and when it's predicted failure, so that means when it's predicted to buy and when it's predicted do not buy. And basically the basic idea is that we will take when the flight experience is lower than 10, then we assume that our prediction will be do not buy, failure, while when the number of flying experience is 10 or more, then we will assume that the prediction for this client is 1. Okay, that's the result of choosing the cutoff at exactly at 10. Watch out that here it is classes, basically division. You know, there is written 2, 4. This is the upper value of the classes, but it means that for example these 34 clients with who did not buy, and these 3 clients with they have flying experience 0 or 1, and then in the second class you have the clients that they have experience 2 or 3. Okay, so 4 is not included. This means that on this line you have basically the clients with experience 8 and 9 and not 10. So here the prediction by this will still be do not buy. Okay, probably it would have been better to make inclusive this upper bound here, but okay, I have chosen for this way. Now, so let's now open the Excel file that you can also find on Brightspace with the title "The Problem of the Binary Statistical Classification," and let's try to calculate the confusion matrix as is asked in question 1. Okay, here we are, and so let's try to derive this confusion matrix by making some of the calculation automatic with Excel. So and first I reproduce the table here on the left side, on the right side, in a more broad version. So I put here again equal to 2, and then equal to this plus 2, then I take it down. Okay, and I call this t variable. This is often done also in literature. Okay, so this is the value where they have to choose the cutoff, and we said also that the cutoff, that must be chosen at 10, so this. Okay, then I want a column where there will be the prediction. Okay, so the predicted. And since I want to fill this column automatically by using the cutoff definition, then I create here on column G another column, which is basically where the value is given by the difference between the column, the variable, and the cutoff. Okay, where the cutoff must be constant when I extend the calculation. Okay, so you see that basically what I get is I get a negative value until 8, and then a 0 value, 10, and then I get a positive value. And so because I know that let's say for the clients with in this region from 12 to 20 basically, then these are 10 or more flight experiences, then I have predicted 1. So I can fill this column in this way by doing let's say with an if, and I will say this function if, so if this is larger than 0, then the predicted value is 1, otherwise is 0. Okay, and then I extrapolate this to all the column, and so you see that basically only from this line here we get a predicted 1, so success prediction, because from here on we have clients with flight experiences larger than 10, equal to 10 or larger than 10, because I recall you this class 12 means 10 or 11 flight experiences. This means 12 or 13 and so on. Now next to this column I put the two columns don't buy and buy, which basically are now our column failure and success, and then I take it over, so this column here and this other column by here. Okay, so now I can calculate the different probabilities, so true negative, false positive, false negative, and true positive, and I will put them here in other columns. So I create these columns and I give them also a color in order to the headers, in order to remember that they are indeed the same as what occurs here in the matrix. Okay, now let's try to fill in these columns. So for example, you see that the true negative basically are represented by these clients. So we want in this blue column, true negative, to get only those values. So you see that what I can do, I can here multiply basically the column failure times, and then I want to have only the first and not the last ones. So you see, if I multiply by 1 minus and then the value of the prediction, then here I will get 34, and I will still get everywhere the correct number of true negatives, because it are only up to here to 123, because these other, they are predicted to buy, so they are not true negatives. And here also I can take the sum of all the true negatives, so always with alt equal, and then I get this value 413. Okay, and I color also this cell. Okay, then I have to fill the column false positive. So who are the false positive? False positive is the clients which are predicted to buy, but actually we don't buy. They don't buy. So basically they are this one. So you see that I can then fill this column just multiplying the column failure times the predicted, because then I will get only the false positives. Oops. You see, and which are these ones. So here I can also take the sum, and I get in total 114 clients. Okay, let's then move to the false negative. Who are the false negative? The false negatives are people which are predicted not to buy, so predicted 0, but they actually buy. So basically they are those people here. So you see, in order to get this column correctly, false negative, then we have to multiply here the success column times again 1 minus the predicted column. Okay, so here I get here 3, and then I move this downwards. Okay, and then I get all here. I can sum up all the false negative, actual alt equal, enter, and I get 58, and I color this in green. Okay, eventually we have the true positive, so people which is predicted to buy and actually they buy. So you see basically there are these ones here, and so in order to get this column true positive correct, then you see I can just multiply the success column times the predicted value, and so here we get 0, but in the case of the true positive I will get the proper number. Oh, again. Okay, and here I also have to sum up, so alt equal, enter, and I get 221, and I color this in red. Okay, then now I can move these values inside my matrix. So this will be 413, false negative will be equal to this, false positive gray, enter, and then true positive equal to the red. Then I make somehow the total sum here, the marginal value. So here I will have the summation of true negative and false positive, basically all the observed they don't buy. Here I have all the observed that they buy, so equal to 58 plus 221. Okay, I check that together they must be equal to the total, because everybody either buy or not buy. Okay, and the same here is for the predicted. So the predicted do not buy. Here I have true negatives plus false positive, and here the predicted to buy, all of them equal false positive plus true positives. And here I have also to check that the total amount of this plus the predicted positive must be also equal to 186. Okay, so we see in this way we have completed the confusion matrix for the given value of the cutoff of 10. We can color also this in evidence. Okay, and of course I choose for the long way for the simple reason that the way that I have constructed this calculation, I can change the cutoff and then I will immediately get the result, the confusion matrix for a different value. So for example, we see if we instead of A6 here 10 we choose 8, then I get everything get immediately adjusted to the new calculation. Okay, and this is reasonable because of course the choice of the cutoff is arbitrary to some extent, and then it is obvious that you would like also to check what will the confusion metric is and the measures that we are going to calculate in the following questions for a different value of the cutoff. So let's restore here the value of 10. So because the exercise we are doing is about the value of 10. Okay, then in the following question, number 2, we are asked to calculate the following measures, basically the sensitivity, the specificity, and the false positive rate, or it's called also the fallout. Okay, let's implement this in our Excel file. Okay, and then if I recall the definition, you remember that if I told you also last time, if for the sensitivity, you remember that this is the true positive rate, and it's very easy immediately from the confusion matrix to get this value, because the true positive rate is just equal to the true positive amount divided the total observed positive. Okay, and then we get this number, which is better to round off only with 3 decimals. So choose here. So and then this is 0.792 is enough. Then the true negative rate, the specificity, is also easy to remember how it can be calculated from the matrix, because it's the amount of true negatives divided the total observed negatives. So they did not buy, and yes, in this case we can round off only with 3 decimals. Oops, here it was not on the correct cell. Okay, so we get 0.784, and for the fallout, we know this is the false positive rate, so I have to divide the false positive with the total sum along the vertical column observed failure, and this is this number which we know. Okay, first I round this off. We know that this must be also equal to 1 minus the true positive rate. We can check if I do here 1 minus the true positive rate, I get also, the true negative rate, 1 minus the true negative rate, this must be equal to the fallout. Okay, indeed. Okay, so you see that in the case, basically the outcome of this calculation is that choosing the cutoff at 10 or more, then I get a reasonably high value for sensitivity, true positive rate, and specificity. And of course, since the false positive rate is just 1 minus the true negative rate, then of course a very high specificity means small fallout. Okay, why did we concentrate on these 3 measures? Because in the next question we introduce an index which is called the Youden J index, which, if we look at the theory part, is given by this definition, just that the index J is given by the sensitivity, the true positive rate, plus the specificity, plus the true negative rate, minus 1. And since 1 minus specificity is also the fallout, then the J can be expressed as the difference between the true positive rate, the sensitivity, and the fallout, the false positive rate. Okay, this J index basically describes the magnitude of the probability of an informed decision between the two classes. Okay, let's first calculate this index in our case. Okay, so basically we have this index J is then given, according to definition, by the difference between the true positive rate, the sensitivity, and the fallout, the false positive rate. And so in our case we get 0.576. And of course we must understand what does this mean. I mean, is this index high or low? And if we look just at the definition, then we see that the index J can vary between 0 and 1. Okay, it ranges from 0 and 1 inclusive. What does this mean? Okay, consider that in the theory of the decision, the reference is not the ignorance, but the 0, let's say, level is when you take a decision based on purely randomly. Okay, so basically what we expect is that at the chance level of performance of a test, we expect the value 0. And this actually occurs when, for example, a diagnostic test gives the same proportion of positive results for groups with and without the disease. So basically, this is equivalent to say, if you will make a test just throwing a coin, then you will expect both, basically, those two values equal to 0.5, and then you get 1 minus 1, and then you get 0. So basically the 0 value of J, it means that is equivalent to make a test just throwing a coin. A value of 1, see, when I have a value of 1, when basically if there are no false positive and no false negatives, then basically when the test is always correct in the prediction, then you see I get 1 plus 1 minus 1, and then I get a value of 1. And in this case, of course, the test is perfect. So consider that we got a value of 0.57, almost 58. So you see that we are very far from chance level performance. So our test is definitely good, but okay, it has it does not approximate 1 at all. Although we saw that this test had a very high specificity and sensitivity. So if you look at this formula, consider also that there is a pathological case, and basically when basically a test gives only false negatives and false positives, okay, then in that case you get J equal to minus 1, but then this just means that positive and negative labels have been switched. So if we should get something like this, then you just change false positive to false negative and the other way around, and then you will get a correct range. This is a subtletive, but it's not very important for us now. Okay, in principle we are ready with this exercise. And of course one could ask, but why is this? I mean, I could have also other to make other indices. Why I've chosen for this J statistics index? The reason is very simple, and is important for aviation students, because you see that this J is given by the difference between true positive and false positive. So you know that if you consider, for example, in a maintenance process, that the detection of a false positive implies some cost, while the detection of a true positive then implies some benefits. So you see that this difference between J as true positive rate minus false positive rate, it is just let's say gives the trade-off between benefits and costs. And we are going to explore this in the next exercise, where this trade-off between true positives, these benefits, and false positive costs will be illustrated in a diagram which is called the ROC curve. And what we are going to do is to extend this calculation, cost benefits calculation, like we did in this example for one value of the cutoff. Then we extend this calculation to all possible values of the cutoff, and then making a plot of this cost benefit curve, then we will derive this ROC result. Because you see, I mean, why a false positive means cost? Because if you have somehow a false alarm, and then you think that the system thinks to have detected some failure in for example, in functioning of some part of the airplane, then you have stop flying, and you will not make revenue. Okay, so this implies costs. While the detection of a true positive, let's say the detection of some issue, will prevent you to lose money in the future, and then it represents a benefit. Okay, so that's also, to conclude, is also the reason why I did this calculation in such a way that I can change the cutoff, and then to reproduce automatically all the values of the confusion matrix as well as of the measure, just changing one parameter. So for example, if we change this 10 again to a different value, for example 8, then you see that I get for the J index 0.42, which is lower than 0.57. So at least you see I can immediately conclude that the decision is better informed in the case of cutoff at 10 instead of at 8. But okay, let's explore this in the next exercise.